In this third class of Chapter 5 of the course of Basic Geometry, I present the following topics: circumference inscribed in a triangle, circumference inscribed in a quadrilateral, circumscribed circumference of a triangle, circumference circumscribed in a quadrilateral, arc minor and arc major, inscribed angle, right angle, tangent chord angle. In this first slide of this third class of Chapter 5 of the Basic Geometry course, it presents the definition of the circumference inscribed in a triangle. The figure 5.23 shows the triangle ABC with a circumference with center C inscribed in the triangle. That is, the circumference has 3 points of tangence on the 3 sides of the triangle. The center of the circle inscribed in a triangle coincides with the meeting of the 3 bisectors of the angle, divide the triangles into 2 angles of equal dimension. Drawing from the point of tangence on each side a perpendicular line segment, the 3 perpendicular segments will find the center of the circumference C. In the second half of the slide, there is a quadrilateral inscribed on a circumference. The center of the circumference inscribed in a quadrilateral coincides with the intersection of the 4 bisectors of the 4 angles. Drawing from the point of tangence on each side a segmented perpendicular line, the 4 perpendicular segments will find the center of the circumference C. Note all quadrilaterals have a circle inscribed with 4 points of tangence. An example is the rectangle quadrilateral. For a quadrilateral to have an inscribed circumference, it is necessary that the sum of the dimension of 2 opposite sides is equal to the sum of the dimension of the other 2 opposing sides. This slide presents a definition of a circumference circumscribed to a triangle. Figure 5.25 presents a triangle ABC and a circle with center C and with the curve passing through all the vertices of the triangle. The center C of the circumference coincides with the intersection of the 3 perpendicular bisectors of the sides. The second half of this slide shows a circumference that circumscribes a quadrilateral. The curve of the circumference passes in the 4 vertices of the quadrilateral. The center of the circumference coincides with the intersection of the 4 bisectors of the sides of the quadrilateral. For a quadrilateral to have a circumscribed circumference, it is necessary that the sum of the dimension of the opposite angles be supplementary, that is to say, the sum of the angles of opposite vertices have to be 180 degrees. This slide shows the definition of a minor arc and a major arc. The figure 5.27 shows a circumference with center C and points on curve A and B. We have a central angle S with range connected the center point to points A and B of the curve. In this way, 2 segments are formed in the curve. The X segment is the smallest curved part. This section is called the arc minor. The part of the curve formed by the arc Y is called the arc major. If the center angle had a value of 180 degrees, both arcs would have the same value equal to a semicircumference or semicircle. When nothing is said about an arc defined by 2 points on the curve, it is assumed that the reference is to the arc minor. In this slide, the concept of inscribed angle is defined. An inscribed angle of a circumference is an angle with the vertex in the curve of the circumference and the two straight lines secant to the circumference. In the figure, the AVB angle, called the R angle, is an angle inscribed to the circumference. The angle ACB, called the angle S, is the central angle corresponding to the arc AB of the same inscribed angle R. The value of the angle R has a value half of the value of the angle S, both corresponding to the same arc AB. The figure 5.28 shows a circumference with center C and 2 points on curve A and B. The 2 points on the curve define the center angle S. But if from any point of the curve, for example point V, we draw two line segments connecting this point V to the points A and B, we will have an angle formed by two line segments called the angle R. At this angle formed by the two line segments coming from the point V of the circumference we call inscribed angle. The value of the inscribed angle is half the value of the center angle corresponding to the same 2 points A and B. This slide is presenting the proof that the angle inscribed on a circumference has half the value of the center angle corresponding to the same 2 points of the curve. The figure 5.29 shows a circumference and the central angle S covering the curved section composed of points A and B. Also is presented the inscribed angle R whose vertex is the point V, and that is formed by two segments of secant lines that connect the point V to the points A and B. To carry out the proof, it is drawn the straight line segment VD, which is an auxiliary line segment that matches the diameter VD. In this way, the central angle W, S, and T are formed. The sum of these three central angles sum 180 degrees. The triangle VCA is an isosceles triangle that has two sides equal to a radius. Thus, we have two angles equal to the value of R plus U. The non-equal angle of the isosceles triangle is the angle WU. Thus, by the definition of the sum of the interior angles of the triangles, we have that the sum of the interior angles is equal to 2 times the value of the angle of R plus U, plus the value of the angle WU, resulting in 180 degrees. Then the value of the angle WU is equal to 180 degrees minus the double of the value of the angle R plus U. The substitution of the value of the angle WU in the expression of the sum of the three central angles results that the sum of the value of the angle S plus the value of the angle of T is equal to 2 times the sum of the values of the angle R plus U. But the triangle VCB is also isosceles, since it is formed by two sides equal to the radius and has two equal angles to the angle U. Then we have that the sum of its interior angles is given by twice the value of the angle U plus the sum of the angles W plus S. However, the value of the angle W plus S is equal to 180 degrees minus the value of the angle T, because the angle WU plus S are supplementary to the angle T. Hence result in the expression saying that twice the value of the angle U plus the supplementary angle 180 degrees minus T equals 180 degrees. This expression results that 2 times the angle U is equal to the angle T. Substituting this last expression in the anterior expression finally results that the angle S has a value of 2 times the angle R. That is, the inscribed angle R has half the value of the center angle S. This slide shows an inscribed angle with a 90-degree value that is a right angle. According to the anterior demonstration, the center angle corresponding to this inscribed angle is a center angle value with 180 degrees. That is, both radii form a diameter corresponding to the hypotenuse of the triangle formed by the three vertices A, B, and V. Therefore, the segment AB is the diameter. The AV and BV legs, or catheti, form the inscribed angle. As a central angle formed by the center of the circle and the 2 points A and B has 180 degrees, the value of the inscribed angle will have the value of the half of this value, that is, 90 degrees, which is a right angle. This slide shows a tangent chord angle of a circumference. Figure 5.31 shows the tangent chord angle, that is the angle BEG. A tangent chord angle of a circumference is formed by a tangent to a point on the circumference and a secant straight line originating at the point of tangents. The tangent line segment consists of the line segment AG, and the secant straight line segment is composed of the straight line segment AB, forming the tangent chord angle R. The central angle encompassing points A and B of the curve, called the angle S, has twice the value of the tangent chord angle R. In this slide, it shows that the value of the center angle S is twice the value of the tangent chord angle R. To perform the proof, it is observed the triangle ABC formed in the figure. This triangle is isosceles and has two equal sides to the radius and the chord AB. As it established that the sum of the interior angles of a triangle is equal to 180 degrees, we have that the sum of the two times the value of the angle T plus the value of the angle S result in 180 degrees. On the other hand, the radius AC is perpendicular to the segment of a straight line AD that by definition is straight line tangent. Then the sum of the values of the two angles R and T results in 90 degrees. Then you have the expression that the value of angle T is equal to 90 degrees minus the value of angle R. Substituting in the interior expression corresponding to the sum of the interior angles of a triangle, it turns out that the value of the central angle S is equal to twice the value of the angle R. Thus, the central angle called S, corresponding to the arc AB, has twice the value of the tangent chord angle R.